Section 2.4, the limit of a function. We have two objectives in this section. First of all, we want to define limits and use limit notation. And second, we want to evaluate limits, and that includes one-sided limits, using graphical and numerical approaches. Why are we specifically stating that we will find limits using graphical and numerical approaches? Turns out that there's actually three different ways we can find limits, either numerically or graphically or analytically. In this section, we will focus on the first two, and we won't do any problems analytically. That's the more advanced technique that we will use in a later section. So before we get into it and explain what's going on, let's try to understand the concept of limit and what it actually is doing. So first of all, we are going to always begin with some kind of function f of x. So in this case, I'm going to draw some function f of x on the xy plane, and I'm going to specify a point called x equal to a on the x-axis. So in this case, I'll pick that point there to be the point I am interested in. So when I write limit as x approaches a of the function f of x, what am I really asking for? And so here's what I'm asking for. I want you to pretend for a moment that this function is like a highway, and you are walking or driving along on this highway, either from the right to the left or from the left to the right. So you're walking along this highway, and we want to know what your destination is. So the destination in this case is the place where x would be equal to a. Can we predict what your destination is without seeing you get to the destination? So like f of x is a highway, and can we make a prediction from your driving where you're going? If we are able to make that guess, we call that the value L, and that value is a number on the y-axis. Now, how do we do this? Obviously, I cannot start looking at you driving from way over here. That's way too far. What I need you to do is to be really close to x equal to a, either before or after, but not at a itself. So if you've already reached your destination, it's too late, I lost the game. I need to know what's happening before you get to the destination, and I'm allowed to look at you all the way through until you are in the destination. So I can look at you here before or after the value that we're calling x equal to a. So using those numbers, can I predict where you're going, right? So if I can predict where you're going, I call that capital L. But if I can't, then either you don't have a destination or the destination does not exist. Maybe you fall off the cliff or something, hopefully not. But basically, that's what we mean when we're talking about the concept of limits. So how do we read this here again? We read it like the limit as x approaches a. So this is telling us where to look on the x-axis. It tells us the name of the function f of x next. And your job is going to be to predict the number that we're calling capital L. Sometimes that number exists, sometimes it doesn't. If it's a real number, it must exist, and it's going to be unique. Now, the technical definition is written over here on the middle of the page. I'm going to leave it and give you a second to read it on your own, but let's begin by looking at a specific problem where we actually have a function called f of x. And in example number 1, it says use the numerical and or the graphical approach to estimate the limit as x approaches 3 of the function f of x if it exists. And the function f of x is this guy right here, x squared minus 5x plus 6, all divided by x minus 3. Now, why did they specifically write x approaching 3? Why can't I just plug the random number into the function and see your destination directly? Well, that's a good question, because if I were to put 3 into the denominator, then I would end up with a bunch of random numbers on top. Who cares what they are? Some random numbers. You put in 3, it's going to be 9 minus 15 plus 6. It's some real number, but on the denominator, if you put 3, you end up with 3 minus 3, which is in reality 0, and you cannot divide by 0. This is not a real number. And so this is why we're having to use the concept of limit to estimate what the destination or what the y-coordinate should be. This is the reason why, in this case, the 3 is in the middle of the table, and we are questioning what's going on at x equal to 3. Right? We can't plug in 3 directly into the function, so we fall back to the concept of limits. Now, how can I find out what's going on at 3? How can I make an educated guess? Well, if I'm not allowed to plug 3 in, let's plug some randoms before and after 3. So plug random numbers before and after 3 to make a prediction about what's going on at 3. And we can do this very easily with a calculator. Calculators can evaluate numbers really, really fast. So let's take the function f of x and plug the function f of x into our calculator and use the trace command to see if we can fill the table up with some random numbers and predict the limit of the function f of x as x approaches to 3. So once your calculator is turned on, go to the Y menu where we always graph everything, and let's plug the function. In this case, it has a numerator and denominator, so make sure you use some parentheses around everything. So in this case, I'm going to have parentheses x squared minus 5x plus 6, all divided by parentheses x minus 3, close parentheses. And I'm going to click zoom, then I'm going to pick the standard window, which is option number 6, to get a graph. So it looks like a nice straight line so far, and we want to know what's happening at 3. So if I click on trace, then click 3 itself, you'll notice that the calculator does not return a number. At the bottom of the screen, it says x equal to 3 and y equal to, and it has no numbers. And why is that? That's because of what we explained a few seconds ago, right? If I put 3 in the denominator of this function, I'm going to be dividing by 0, and that is not allowed. Okay, so if I cannot trace 3 itself, can I trace, for example, 2.9? That's pretty close to 3, but not exactly 3. And yep, apparently the number is 0.9. So if I go back to my notes, I can write that when x is equal to 2.9, the y coordinate is going to be 0.9. Okay, perfect. Let's do this again with 2.99. So what's going on with tracing 2.99. What do I get for that? Well, I get 0.99. So, okay, great. Let's transfer that back to over here to our notes. Again, 3, we don't have an answer so far. That's why we're using limits. We need to predict, and the calculator can confirm. If I trace 3 itself, nothing happens. I don't get an answer. But what about the next number, which is 3.01? Okay, so 3.01, tracing that, I get 1.01. So 1.01, and finally, let's do 3.1. So 3.1 is going to give us 1.1. So the last value in this table is 1.1. And remember, you can make your table as big as you want. You don't have to pick these numbers specifically. As long as you pick numbers sufficiently close to 3, meaning very, very close to 3, then this method is reliable. If I try to put in here, for example, 3.7, then that's not reliable anymore because 3.7 is really, really far from 3. So think of numbers like 3.0001 or 3.00527, I don't know, 3.0000012, or things like, I don't know, 2.99782, for example. Some random numbers that are really close to 3, but not 3 itself. Now, by looking at all these numbers that you just filled in the table, can you make a prediction about the number in the middle? So what number might be there? So if I'm noticing correctly, I'm seeing 0.9, and in my head I'm thinking that's like a 1 almost. 0.99, that's even closer to 1. That guy 1.01 is pretty much like a 1, and then finally 1.1 is almost like a 1. So if I was a betting man, which I'm not, I would say something like the limit as x approaches 3 of the function f of x is equal to 1. So if I were to put a number here, I would say that that number should be 1. And that's basically the end. That's how you do the problem with the numerical method. You just plug the numbers into the function and you plug enough numbers until you see some kind of pattern. Now, again, you can do this with a table or you can do this with a graph. And in my case, the function passes through the point 2, 0. The function passes through the point 4, 2, and so on and so forth. We get those values from the calculator using the trace feature, and we can now graph our function on our notes. So as long as you just make a line that passes through those 2 points, you're good to go. keep in mind the line has a hollow point at 3, so this is an open point, and that's why we are interested in finding the limits as x approaches to 3. So the function is some random line, and it does not have a y-coordinate when x equal to 3 because the point there does not even exist on the graph. So again, the idea is use the numbers before 3 and after 3 to make a prediction about the y values on the curve. And it turned out that all of these y values around here, they all were approximately equal to 1. That's that number on the y-axis. Since they were all approximately equal to 1, we will say that if we were ever to reach 3, then 3 would give us exactly 1. So that's the concept of limits. Now, sometimes we want to focus on just coming towards 3 from one side, and that's what we call one-sided limits. So if I was to restrict you to come to 3 just from this location, so just come from the right to the left, that would be called a one-sided limit, and we would write something like this: limit as x approaches 3 with the little plus sign, and we would write f of x. So what does this notation mean? What does it mean to write 3 with the little power, the plus power? It means I want you to walk from the right side of the graph towards 3. So walk from the right to the left. Don't touch 3 itself. Tell me what the y-coordinates are going to be. And similarly, if I were to write something like the limit as x approaches 3 minus, so now it's like a power, but it's just a minus sign of f of x. What do I mean by that? It means I want you to come towards 3, but select numbers slightly smaller than 3. So pick these guys over here. This is again called a one-sided limit, and this time you're walking from left to right. So pick those numbers only specifically and tell me the y-coordinates of those guys. So that's what we call one-sided limits. So the key point is to remember, if I put 3 plus, I'm telling you pick numbers bigger than 3. And if I put 3 minus, the numbers you are going to put in your table are going to be smaller than 3 itself. Okay, so that's what this new notation means, and that's what we call one-sided limits. So to summarize, 3 plus and 3 minus are not specific values. So when I say 3 plus, you should start thinking in your head 3.01, 3.00005, or 3.0000012, and things like that. So pick a bunch of random numbers in your head that are slightly bigger than 3. Don't go picking 3.5. That's way too big. Your number should be, for all intents and purposes, like a 3. So if you rounded it, it should be basically a 3. And when I say put 3 minus, what do I want you to think about? When I say 3 minus, I want you to think of numbers slightly smaller than 3. So like things like 2.99999 or 2.97814, for example. And the list goes on. There's a lot of these numbers. So pick one of those and test with that kind of number what the limit should be. So let's go ahead and practice this one more time. So in this example number 2, we have the function, and we're asked to find a limit again. And it says again, use numerical and graphical approaches to find. In this case, we're looking for the limit as x approaches to 2 on this function f of x, if it exists, because it may be not possible to find the limit. And we are given that the function f of x is this absolute value of x minus 2 divided by x minus 2. So why am I again interested in the limit as x approaches to 2? Well, think about that for a second. If I were to put 2 in the numerator and in the denominator, I'm going to end up with 2 minus 2 and absolute values on top, and then 2 minus 2 on the bottom. So that's basically 0 over 0, and you cannot divide by 0. And that's why we're having to do all this extra work, because dividing by 0 is not allowed. It's not going to result in an answer. So we want to know what's happening in the middle of the table. And again, I'm choosing the numbers specifically for you so that we can all have matching answers. But in general, these top numbers can be left out blank, and you'll have to go and select your own random numbers. And in this case, since you care about the limit as x approaching 2, regardless of whether it's from the left or right, pick random numbers before, then pick random numbers after. And so an easy, nice way to build the table is to put 2 in the middle and decide I want 3 numbers before, 3 numbers after, or like 2 numbers before, 2 numbers after, and make the choices afterwards. So that 2 is in the middle, and the numbers smaller than it are on the left side, the numbers bigger than it are on the other side. So again, just like we did in the previous problem, we're going to use the numerical approach first. I'm going to go ahead and put this function into my calculator and evaluate what's going to happen. So going back to my calculator screen, let's go to the Y menu and clear the previous example. And let's begin by putting absolute values. In order to access absolute values, I got to click the math button, then move over to the column called numbers, and option number 1 says absolute. I'm going to write x minus 2 next and close the absolute value, then divide by the denominator. My denominator also has multiple terms, so I'm going to put again x minus 2 in my calculator, and I'm just going to click enter. Now this time I'm going to do something a little bit different than before. I'm not going to show you the graph. You can click on graph yourself and see what the graph looks like, but I want to show you an alternate method for finding the solutions that go inside of this table. So this is another tool, another something that we can use on our calculator. And first we'll need to set up some stuff. So first click second and then click the window key. So second and window key will open up this menu called the table setup. And what we want to do is use the down arrow to go to the line that says INDPNT, which stands for independent. So you're going to go down a couple times, and what you're going to do is you're going to move the highlight from auto to ask, then click enter. So ask should be blinking for you, it should be highlighted, and to test we can click second window again and see that it's been saved. So the independent should be on ask, the dependent should be on auto. Now, what that is doing is basically preparing the calculator to accept some random numbers from us, and in return is going to give us the y coordinates. So let's click second and graph, not just graph, second and graph, and that will give us a table, and that's what we are interested in seeing. So we want to know in this problem the limit as x approaches 2. So what I'm going to do is put some random numbers in this table that are not 2 itself, but they're slightly smaller or slightly bigger. So in this case, the table is written vertically. On our notes, it's written horizontally. But let's begin with 1.9, for instance. And when I type in 1.9 and I hit enter, I get -1. So if I type in 1.99, again, I get -1. If I put 1.999, again, I get -1. Now, if I put 2 itself, notice what it does. It says error. That means that there is no solution, and that's why we're having to do this whole limit, remember? Now, what about 2.001, for example? What do I get? Well, I get 1. What if I put 2.01? I get 1 again. What if I put 2.1? Again, the answer is going to be 1. So transferring this data to our table, we can see that if the number is smaller than if the number is smaller than 2, the number is always -1. But if the number is bigger than 2, the answer is +1 and +1. So knowing all this information, can we decide what the limit as x approaches 2 will be? And unfortunately, there is no pattern. If you come from one side, the numbers are pointing to -1, but if you come from the opposite direction, the numbers are giving us a completely different number. The numbers here are 1. So what does that mean? That means that this limit does not exist. So the limit as I approach 2 on the function x minus 2 absolute values divided by x minus 2 does not exist. And I'm writing D and E for does not exist. Okay, so let's investigate why by looking at the graph. So let's see the graph. Going back to the calculator, just click on graph on your screen and you can see that the graph is made up of two horizontal lines. So if I come from the left to the right, I'm walking on this really low line where all the y-coordinates are -1. But if I come from the opposite direction, so if I come from, for example, 5 towards 2, you'll see that all the y-coordinates are always 1, and that's a different value from the bottom line. So in other terms, whoever decided to build this highway did not plan it correctly because the two branches of the highway are not connecting. As you can see, we will fall if we try from one to the other. We are falling off the cliff and we're ending on the other highway, basically, right? So that's an example of a situation where the limit won't exist, and that's because there's a gap, a massive, massive gap, unlike the previous problem where the gap was like a little hole, and you can just patch it with some concrete or some asphalt. Here, the highways are not even the same city, basically. One of them is resulting in the y being 1, and on the other side, the y's are always -1. And that's why we are saying that the limit in this problem, it does not exist. Now, one thing we can say about this problem is that if I come on the highway where the numbers are slightly bigger than 2, so we're talking about all of these guys over here, we can say that that limit does exist. If I go only from one side on this function f of x, then all the answers point to 1. However, if I decide to come from the other direction, where the numbers are slightly smaller than 2, that's why I'm writing the 2 minus. It's all of these guys over here. Their value also does exist, right? There is a limit for the function there, and the function has a limit of -1. However, if you leave it up to me to come from the left and right and choose my own road, then I won't get a destination. I'll go to 2 different locations, basically. So the one-sided limits always exist, but the actual limit without the plus or the minus may not exist. So in summary, for the limit to exist, what needs to happen is the one-sided limits have to give us the same number, and that number is the one we would write there. If the one-sided limits are not resulting in the same value, then we say that the limit of the function f of x, it does not exist. And the last thing I'm going to do here is just draw the picture that we saw previously on the calculator. So if I pick any number bigger than 2, I'm always seeing a highway that looks like this, right? So these are all the points where x would be bigger than 2 itself, and their y-coordinates was always 1. And on the other hand, if I pick the other direction, if I walk to the 2 from the opposite side, I see different values completely. So my highway takes me to a different location. And so we can't make a prediction about your destination. Your prediction depends on which highway we're walking from. If you're walking on top highway, then your destination is going to be 1. But if you're walking on the bottom highway, your destination will be -1. So in general, we cannot predict your location depending on where you're coming from. So these points both are hollow in this case. There is no answer to the limit or to the y-coordinate when x itself is equal to 2. So this is kind of the worst case scenario. The function does not exist at 2, and there is no limit at 2 either. So if you were to complete this table, what would you put in the middle? You would simply say no solution or that the limit does not exist. Okay, so that's the end of that one. Let's take a look at the next one. So in this next one, we are given a function with multiple pieces. So they're saying that the function looks like 3 when x is bigger than 0. So what does that mean? That means they want me to draw a horizontal line. The function is always 3 if the function has an x-coordinate that's bigger than 0. So does not include 0 itself. There's an empty circle there. That's because this inequality does not have an equal sign. Now, on the other hand, they're telling me that the graph looks like -2x when x is less than or equal to 0. So if I put any of these random numbers that are slightly smaller than 0 or bigger than, slightly, so to the left of 0, like -1, -2, -3, and so on, the graph is represented with the -2x line. And so let's just do a couple of points. When x is 0, the value would be 0. We're allowed to touch 0 in this case because there's an equal sign. So that's why I'm putting a solid point here. So this is a solid point, and this one is a hollow point or an open point. And let's say x is -1. If x is -1, the y-coordinate would be -1 times -2, which would be just simply 2. And we can connect the dots to see what the graph looks like. So it's a funky looking graph, and that's why I'm having to do it by hand. The calculator can graph these piecewise functions, but it's just easier for me to do it here by hand. Now, once we have finished doing the graph, the question is asking us for the limit as x approaches 2. So we want to know what's the limit as x approaches 2 on this function f of x. We also want to know what the limit is when x approaches -1 on this function f of x. And finally, we want to know what the limit as x approaches 0 is on this function f of x. So the way we read this is we always read limit, then x approaching the value, 1 to 0, whatever, and then we say the function f of x at the end. So we read limit, then the x, then the function. So for the first one, what exactly is going on there? So it's telling me to look at the place where x is 2. Don't look at 2 itself, look before and after. So these are these sections on the x-axis, and they want me to make a prediction about where the highway would take me. So if I was to walk on this highway, basically, either on the left side of 2 or the right side of 2, it does not matter. If I were to walk on this highway, where would I get eventually, right? So pick any of these numbers and tell me what your destination is going to be. Well, it's kind of obvious. The highway is always at the height of 3. The y-coordinates of any point there is 3. So it seems like a good answer would be to say that this limit is simply 3, because all the points on that side of the graph have the same y-coordinate. So it doesn't matter if I'm at 2.5, the y-coordinate is going to be 3. It doesn't matter if I'm at 2.01, the y-coordinate is going to be 3. It doesn't matter if I'm at 1.99, the y-coordinate is going to be 3 again. It's always 3, no matter what. So that ends the first one. So the first problem is basically finished. And now let's look at the second one, where the limit is approaching x equal to -1. So where is x equal to -1, first of all? So I'm interested in knowing what's going on there. So that's basically here. So don't touch -1, but try to predict what the y-coordinates are going to be. So this time you're along this other highway right here, and you're walking towards -1. Don't touch -1, so you're allowed to be a little bit before or a little bit after -1, but not at -1 itself. Can you predict what the y-coordinates are going to be? And I think we can, yeah, why not? I mean, at -1 itself, we got a 2 earlier. So if I'm a little bit before or a little bit after, I should be probably around 2 as well. I mean, that's what makes sense, right? If -1 is allowed as input of the function and it's given me 2, then when I put a number before or after, I should pretty much get the same output again, which is 2. So for both of those problems, it doesn't matter if you're walking from the left or from the right, the limit does exist. Now, the third one is a little bit tricky. And why is it tricky? Because this time we're trying to approach 0. And so if we're approaching 0 and we're coming from the right side, then our highway puts us up here at 3, right? Those are the y-coordinates. But if we're approaching 0 from the left, then our y-coordinates will be down here. So what does that mean? Well, that means that you're not going to get to the same destination. The highway drops off, there's a cliff, there's a whatever you want to call it, there's a gap, there's a massive gap. It's not something we can like put a little concrete on or patch it with some asphalt and connect the two lines. One line is at 3 and the other line is pointing towards 0. So what does that mean? That means that the limit does not exist for this problem. Now, this is different than saying that if I were to come towards 0 from the right, that's what the 0 plus means. That's all of these guys over here. The limit there on the function that we're working with does exist. The limit is actually going to be 3 if you come towards 0 from the right side. However, if you decide to come towards 0 from the left, that's why I'm writing 0 with the little minus in the power. So if I were to come towards 0 from the right side, that would be these guys right here on the x-axis. Their y-coordinate on the graph is basically almost 0. So the limit there would be equal to 0. The one-sided limits are going to exist. However, they are not equal. And because they're not equal, the original problem won't have a limit. The numbers must be the same on the left and right so that the limit actually does exist. Okay, so in example 4, we have another one-sided limit. So let's take a look at what's going on here. It says, suppose the function f of x is equal to x every time x is not equal to 1, and it's equal to 3 when the x is equal to 1. So for every number in the universe, to get the y-coordinate, just take the same number that you started with. However, if the number is 1 that you began with, then the y-coordinate is supposed to be 3. So first of all, they want me to graph this function f of x. So let's do that. So if I pick the x-coordinate to be anything other than 1, the y-coordinate is identical. So like for example, if I let x be equal to 4, plug that into the function, and you get 4 back. So when x is equal to 4, the y is going to be 4. If I put 3 into the function, then the answer is going to be 3 also. So when x is equal to 3, the y is going to be 3. Okay, what about if I plug in 2? If I plug in 2, the y is going to be identical, 2. So this is sort of giving us a line that kind of looks like this. However, the only difference, the only exception to this rule is if I plug in the number 1 into my function, then I'm supposed to get 3 back. So when I make my line, I have to be a little bit careful. I can draw the line on the right side like this. I can sort of continue the line on the opposite side, sort of like that. However, I am not allowed to touch the value 1, 1, right? So there's a little bit of a gap in my graph, and that gap is caused by this condition over here. It tells me that x equal to 1 will always give you the y-coordinate equal to 3. Okay, so my graph has a little gap or a little hole, and it has an extra 1 dot just floating in space. So this blue thing is the solid point up there, and this is the open point or the hole on the graph. So that's my function f of x. It's kind of weird, but it's missing one point, and that point has been relocated. Okay, so the question to graph the function f of x is done, and now we want to know what's the limit as x approaches 1 on this function f of x. And the other thing we want to know is what's f of 1. So what's the difference between these two notations? So the first one is basically telling me to investigate what's happening before and after 1, but not at 1 itself. We don't care about what's going on at 1 itself there. But this one is basically telling me to find what's happening exactly when x is equal to 1. And when x is exactly equal to 1, that's that location there, x is equal to 1, my graph has the y-coordinate, which is 3. And so we're done. But what about the limit? Well, if I were to walk on these lines on the left and right of 1, so if I were to approach 1 from the left or from the right, but not touch 1 itself, my graph would put me here, and the answer to the limit would be 1. So the limit is different than the function at the locations. All right, so at x equal to 1, we got a 3, but as we were approaching to 1, we were expecting to get to the destination 1, not 3. So Later on, we'll talk about continuity and what it means, and this is an example of where the function is not continuous. And what that means just simply is that we can't graph the whole function without lifting our hand off the paper, right? I mean, we can't graph a line with another line and put a point right there without having to lift the pencil off the page. And that's what we will talk about when we talk about continuity, and we'll describe what continuity is in mathematical terms. But this is a good example to kind of keep in mind. The function here is not continuous. Okay, for example 5, I am given the graph, so I don't have to worry about graphing anything, and they're asking me to find a bunch of limits. So the function f of x looks like a line, it's another line on this side, and there's a point floating out all by itself. So technically, there are 4 branches. There's one branch, here's the second one, here's the third one, and here's the 4th branch. So there are 4 branches in total to graph this function. Now, first, we want to know what's the limit as x approaches 1 plus. So think to yourself, what does it mean to say 1 plus? This means we want to pick numbers bigger than 1. So think like 1.001 or 1.00005 or 1.0000271, whatever. Something slightly bigger than 1. So basically, we're choosing all of these guys. They are not exactly equal to 1. We're not allowed to put 1 itself, but we're allowed to pick one of these guys. And your job is to predict how high is the curve, right? So the curve seems to be around 1. So when I pick any of these values, I'm getting a y-coordinate that's basically 1. Okay, great. We are done with that first one. Let's take a look at the rest of them. So for the next one, it's asking us for the limit as x approaches 1 minus. So what are these numbers? 1 minus. The 1 minus are numbers like 0.9999, for example, or 0.9897215, and so on and so forth. So these numbers are not equal to 1. They cannot be equal to 1 because this is a limit problem, but they're smaller than 1. And so we want to know, if I pick one of those guys, what's the y-coordinate going to be? So to find a y-coordinate, I go up until I find a curve. Once I find a curve, I stop and I turn to the y-axis. And it seems like the y-coordinate there should be just simply 2. Okay, so that's the end of that one. And let's continue to the next one. So we already have 1 for the right-sided limit. So if I'm coming from the right to the left, I got 1. If I go from left to right, I get a 2. And now the question is, what's the limit as x approaches 1 regardless? So remember, this is kind of a double question. So it's like 2 questions in one. It's asking you to not pay attention to the direction. So it's basically saying, if you're coming from the left or the right, do you get to the same destination? And obviously, in this case, I do not get to the same destination, so the limit will not exist. The highway here takes me to a different destination from the highway there, and that's why the limit will not exist. Okay, let's look at the next one. So the next one says, limit as x approaches -1 plus. So what do I mean when I say -1 with the low power plus? So that means go to -1, but stand on the right side of it. So where's -1 and where's the right side of it? Here it is. So we're not allowed to pick -1 itself, just pick a random number to the right side of -1. So these are things like -0.999 or -0.98712, or random numbers just like that one. So pick one of those and tell me what the y-coordinate is going to be. So if I pick one of those, I look up, the y-coordinate seems to be like around 4 approximately. So I'm just going to say that the limit is 4. Okay, so that's the end of that one, and we're completely done with it. So let's get rid of these numbers. And now let's look at the next one, the limit as x approaches -1 minus. So -1 with the power minus. So what do I mean when I say -1 minus? So that means go to -1, but stand on the left of it. So where is that on the graph? It's this location over here. So -1 minus is slightly smaller than -1. So think like -1.0001, -1.00032115, whatever, random numbers like that. And so if I pick any of these numbers, what's the y-coordinate going to be? So pick one of them and look over, pick one of them, look over, pick one of them, look over. Seems like we're always close to 4 again. So again, I'm going to say that the limit is equal to 4. So now they want me to decide what's the limit as x approaches -1, regardless of whether you're on the left or you're on the right. What's the limit of this function? And here's the reason, and here's the answer. Well, these two were equal, and they are both on the left and right of -1. So therefore, that guy here will be the same. So it has to be the same number. So the one-sided limits were identical. They were both 4. So therefore, the limit itself will exist, and it will be 4. Earlier, these two numbers were not equal, and that is the reason why we had no solution for that limit over there. So I hope that makes sense. If not, let's talk in office hours to explain and understand what's going on. Okay, so example 6 is another one of these things. And again, the question here gives us the graph. It's the function f of x equal to 1 over x. It has two branches, one on the left, one on the right. There are two branches, they're not connected, and they want me to investigate what's the limit as x approaches 0 of this function. So to answer this question, I'm going to break it down again into two different limits. I'm going to answer two separate questions. What's the limit as I come towards 0 from the right? And I'm going to try to answer what's the limit as x approaches 0 from the left on this function. And if these two numbers here, well, if they're even numbers, and if they're equal, then I can finally decide the limit that they asked me for. Now, let's, again, try to understand what's going on with this x0 plus. So x is approaching 0 from the right. So pick numbers slightly bigger than 0. Don't pick 1 to 10. You should be picking 0, 0.1, 0.2, 0.0015, things like that. So these are these guys over here. Not 0 itself. 0 is not allowed, just slightly bigger than 0. What's their y-coordinate going to be? And whether you realize it or not, this graph continues going up forever. And this is our first example of a problem that has a plus infinity as its answer. So, by the way, that just means that there is no limit. The limit is not going to exist because if you get closer and closer to 0, the numbers are going to be bigger and bigger. This graph just keeps going up forever, and the closer you are to 0, the higher the graph is. And the way we say that mathematically is we say that the limit is plus infinity. Now, similarly, if I go towards 0 from the left side, so I'm picking things like -0.00000001 or -0.0005 or whatever. That's basically these numbers over here. They're not exactly equal to 0, but they're slightly smaller. Where is the graph going to be? So for any of these numbers, again, you need to realize that this graph kind of continues down forever. So that's why we're kind of making it look like a vertical line. And again, unfortunately for this problem, these guys down here are negative infinity. So the graph just shoots down forever. It does not ever stop going down. So the way we say that mathematically is we say that the answer is negative infinity. Now, these infinities are not even numbers, by the way. So I could have stopped after seeing one of them and written that the limit as x approaches 0 will not exist. But first of all, these guys are not equal. They're not even numbers in the first place. So let's go ahead and write everything down. First of all, they need to be equal for the limit to exist. they're not even numbers, so we can't even say that they're not equal, right? They're not even, there's no 10, there's no 5, there's no 2, it's just infinity. Infinity is not a number, it's just an idea saying really, really big numbers are showing up. So there is no limit on the one-sided limit, either the left one or the right one. Therefore, there is no limit at x approaching 0. So in example 7, we have a function which is the 1 over x squared. So similar to the 1 over x, except the branch is not in the third quadrant. It's not in the third corner. It's actually in the first and second quadrant. So we have two branches on this curve. And again, this line continues going up forever. So imagine it's stretching beyond the page. It just continues shooting up forever on this side and on that side as well. So the question here is to look for the limit as x approaches 1 on the function f of x, and then look for the limit as x approaches 0 on this function f of x. Okay, so to answer each one of these questions, I'm going to break down the left and right limits. So to try to figure out what this limit is as x approaches 1, let me just start by finding the limit as I approach from the left and the right of 1. And you don't have to do that, but since we're practicing one-sided limits, let's keep doing it in case somebody does not know what to do. This is a way to find the answer by breaking it down into multiple little pieces. So first of all, 1 plus, that means stand to the right of 1. Don't stand at 1, stand to the right of 1. Tell me what y-coordinates you see on the graph. So the y-coordinates that I'm seeing on the graph are all approximately equal to 1. So I'm going to write down 1, and I'm going to circle it because that's the answer there. Okay, 1 minus, it's saying go to 1, but stand on the left of it. So pick numbers slightly smaller than 1. These are these guys over here. And again, if I pick one of them and I go up to the curve, I'm going to see that the number is going to be, roughly speaking, equal to 1. So regardless of which one you pick, you have to be really close to 1. The answer is always going to seem like it's a 1. And so therefore, I'm noticing that the one-sided limits are in fact equal. So that's awesome, which tells me that the number for the limit exists and it's actually the same value. It has to be 1 as well because the other two numbers were both 1. So the one-sided limits are 1, so therefore the final limit is itself equal to 1. So great, that's half the problem already finished, and we kind of made it longer than it should be, but that's okay. All right, then what about this one? What's the limit as x approaches 0? So again, I'm going to try to answer the limit from the left and the right of 0 and see if they're equal and decide the final answer. So let's begin by looking at 0 plus. So where exactly is 0 plus? It's slightly bigger than 0. And what's the y-coordinate going to be? It's not even drawn because it's so high. It's so high, I don't even have enough space to fit it all on the page. So that's basically plus infinity. It's really, really high, and if I go across and look at the y-axis, I'm going to see some really, really big number, and the closer I am to 0, the bigger the number is going to be. So the way I say that is I say that the limit is plus infinity. In the same way, if I approach 0 from the opposite direction, from the left side, so if I come towards 0 from this side but don't touch 0 itself, I'm going to see that my graph is going to be really high, and all those y-coordinates are going to be really, really big numbers. The closer I am to 0, the bigger the number is going to be. And in fact, they are all going to be positive infinity also. They're all going to be really, really, really massive numbers. Now, infinity and infinity are numbers, so we can't really compare and say whether they're equal or not. These are two random, really big numbers. So what can I say for 0? Well, in this case, I will say again that the limit at 0 does not exist. It's also acceptable to say it's positive infinity, right? So I can either say it does not exist, or I can say plus infinity. Okay, so what's the difference between this one and the previous one? In the previous one, the limit on one side was plus infinity, the other one was negative infinity, and these are not numbers, so obviously they're not going to be equal. And so therefore, the limit at 0 did not exist. But for 1 over x squared, the minor difference is that both of these limits, even though they're not equal, they're both in the positive direction of infinity, right? These guys are still not the same number because infinity does not represent a number, it represents an idea. And since they are both positive, I can say that the limit at 0 is also plus infinity. But I just want you to know that when the answer is infinity, it still means that the limit does not exist. Just because I can tell that it's going up, it's going in the direction of to the top, it doesn't mean that the limit is there. It still won't exist. Okay? So when the answer is infinity, it's not a real number, and we can say that it does not exist. All right? Infinity and does not exist in this case are acceptable. Okay, the last one, what do we have here? We have 1 over x, and we are asking for something different this time. So this time, the question is to find the limit as x approaches negative infinity on 1 over x. So the function that we're working with is called 1 over x. And we want to know what's the limit as x approaches minus infinity. And also we want to know what's the limit as x approaches infinity, or sometimes we write plus infinity, of the same function 1 over x. So the 1 over x is what's being drawn. It's this graph over here and this graph over here. And they want me to look at the limit as x approaches negative infinity. So what exactly do we mean by that? It means walk to the left as far as possible. So go in the negative infinity direction on the x-axis, so here. So if I could extend this like 1,000,000 miles to the left, I want to stand there at the very end, and I want to decide what the y-coordinates of these guys are going to be. So if you can imagine, this graph extends always to the left forever. How high will that graph be? So as x goes to the end of time towards the left side of the curve, so if x takes on one of these values here at the end, what's the y-coordinate going to be like? And I'm thinking the y-coordinate is going to be almost to 0. It's like going to be like really, really close to 0, but on the bottom side of the y-axis. But who cares? I'm just going to say it's pretty much 0. It's almost a 0. So the x approaching negative infinity implies go to the left side of the graph, as far left as possible. Now, what about the limit as x goes to plus infinity? So this is the complete opposite. If I were to extend the x-axis all the way to the end and move like 1,000,000 miles down the road, I want to know what's going on here at the end of time. When x goes to the very, very end, which there is no very end, it's always going to keep growing. But if I were to take one of those numbers, really, really big numbers, what's the y-coordinate on this graph? So remember, this graph continues going down, 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 kind of like approaching the x-axis but never ever touching it. So here at the end, if there's such a thing, what's the height of the curve? And maybe you already know, well, it's also 0. So regardless of whether you go to the left or to the right, the answer on these limits is both 0. So when I say x approaching plus infinity, I'm talking about go to the right side where x would be really, really big. Tell me the height of the curve. And in this case, the height of the curve, regardless of whether you go left or right, it's always 0. So think of 0 as like the place where the function goes to stabilize. So eventually everything becomes 0, whether you're on the left or you're on the right. Okay, so for part 2, the function is slightly more complicated. It's the 1 over x plus 2 plus a 3 on the side. And again, we want to know the limit as x approaches negative infinity with 1 over x plus 2 on the denominator plus 3 off to the side. And we again want to investigate what's the limit as x goes to plus infinity or just infinity. And again, it's the same function, 1 over x plus 2 plus 3. So what is happening? Again, when I say x approaching negative infinity, I want you to stand all the way at the end on the farthest to the left possible. and tell me where this graph is going to extend to. So let's use the calculator to see this a little bit better. So in my case, I still have the picture from the old problem, so let's go ahead and erase it and replace it with the new picture. So first, I'm going to put 1 divided by the denominator, which is x minus 2. Make sure you put parentheses. Sorry, it's x plus 2, not minus 2. And next to it, we will put a plus 3. So 1 over x plus 2 plus 3, and I'm just going to save that, and I'm going to click on graph. And you can see this is kind of the same picture that I have on the handout. But what I want to do now, this time, is I want to see more of the negative side of the x-axis. So currently, if I look at my window, my minimum x is at negative 10. I want to make it negative 100. So this will really stretch the graph to the left. So check this out. So now there's 100 little notches on my x-axis in the negative direction and only 10 of them on the positive direction. So if I click on trace and I start walking around on this curve, notice that as I go more and more to the left, my x right now is like negative 72, negative 75. Notice what's going on with the y-coordinate. It's like 2.986. It's not exactly 3, but for all intents and purposes, 2.987988, that's basically like a 3. And if I go back again, and instead of negative 100, I change my window to be negative 1000, I mean, that's really, really big. But again, if I trace, it's going to be, again, like we're at negative 600, negative 700 on the x, and look at the y. The y is basically 2.9988. It's not changing. For all intents and purposes, the graph is stabilizing where the y is equal to 3. So if I go in the negative infinity direction, I'm seeing that the graph stabilizes and everything kind of starts to look like a 3, 2.999 whatever on the y-coordinate. Now, let's see what's going on in the positive infinity direction. And so to do that, I'm going to go back to my window, and I'm going to bring back the negative 10 to the x minimum, and I'm going to put x maximum to be like 1000. So there's now 1000 notches in the positive x direction and only 10 on the negative x direction. And again, click trace, and you can see it's putting me at 495 on the x, and the y is 3.002. And if I continue walking to the right, I'm seeing that the y-coordinate is always, roughly speaking, 3. It's never going to be exactly 3, and that's the key. Right? It's never going to be exactly 3, but it's always going to be approaching 3, and that's the reason why we write here that the limit is 3. So if I were to walk all the way to the end of time in the positive direction towards infinity on the x-axis, we see that the numbers also stabilize at 3. So the limits on the left and the right are both 3. So in the future, we are going to say that there is a horizontal asymptote. I'm going to be calling it HA at y equal to 3, and that's because these numbers are both the same. This is not important right now. You don't have to pay attention to that right now, but that's what we're going to be doing later on in the late chapter when we start graphing these functions by hand. We are going to say that the graph is stabilizing, and it's stabilizing at the height of 3. That's going to be given a name. And so you can imagine here there's a 3 line like this, and the graph is getting closer and closer to it as we go further and further to the left and to the right. That's what the meaning of this 3 is.